Good afternoon, everybody, or good morning, or good evening, depending on where you are. Thank you for joining us in this session on OTEC as part of the MARES webinar series. Today, we're very lucky to have Richard Argall talk to us from Makai Ocean Engineering about a very interesting project in Hawaii, which hopefully could be replicated because it has implications for aquaculture and also for desalination as a piece of infrastructure which is integrated into the marine environment. So without further ado, Richard, can I hand over to you? Please go ahead.
Yeah, thank you very much. Yeah, hello everyone, and I heard there's a few from the UK, so that's good news because you'll probably find it a bit easier to understand me. I did actually grow up in Cornwall in southwest England, and I think someone was from Plymouth, so close enough. Not quite over the Tamar, but close enough. And yeah, as per the introduction, my name is Richard Argall. I'm a professional engineer with probably a little bit more than 15 years experience in the marine renewables sector in Europe and North America. I spent some time working in both, everything from offshore wind farms to tidal energy devices and wave devices, various different marine energy technologies, and here at Makai more recently, doing a fair bit on ocean thermal energy conversion, which is what I'm here to talk to you about today. So the business I work for is Makai Ocean Engineering. It's a small privately owned business. We're based in Hawaii. It's 8:30 at night for me, and it's a nice calm winter's evening in Hawaii. And we do have a couple of other offices in other places, and we've got about 40 staff. And we work on a variety of ocean engineering problems. I think we've been around for about 50 years or so. So yeah, today I'm going to talk a little bit about OTEC. Yeah, with that, I'll go on to my next slide and speak up if anyone's got any issues seeing the slides or any questions. Yeah, so you should see an overview page now, and this is what I'm going to talk to today. So we'll start out just talking about ocean energy and the kind of reference frame for deep water technologies, and then I'll touch on seawater air conditioning. It's not OTEC, but it's a related technology, and then I'll get a bit into just the kind of 101 of OTEC. We'll talk about the resource, the history, and the developments, which is the interesting part, and the costs and challenges. Then I want to talk a bit about grazing opportunity, and I'll explain a little bit what grazing is a bit later on, and also I've got a few slides regarding the kind of how OTEC might fit into the hydrogen economy, which is sort of emerging, and then talking specifically about the challenges of hydrogen, and is ammonia a good intermediary of an energy carrier that's perhaps preferable to hydrogen. And then we'll finish up just with some kind of conclusions and next steps. So that's what we're going to cover. So first slide here, ocean energy and deep water technologies. A few different images around, and sort of the edges at the left and right. You've got perhaps what people conventionally think of when they hear about marine renewables. Wave energy device at the top left, it's the Ocean Power Technologies device. I think that's in Hawaii, that one. Bottom left is one of the Magen tidal turbines, which is up in Scotland. It was a project I was involved with. And then to the top right there is a floating wind turbine, and bottom right is a fixed wind turbine. So those are kind of what we're used to seeing. And what we're going to cover today and talk about is deep water technologies, where a lot of these island nations, and certainly it's true for Hawaii and other parts of the Caribbean through the Pacific, they're not ideal for these technologies around the edges here. So the problem being we have quite deep water. We don't have the low-hanging fruit of the North Sea, where we've got shallow sandbanks we can drive piles and put wind turbines in en masse. So we want to exploit the deep ocean, and so the way we do that is with the technology shown in the middle here, OTEC and SWAC. So OTEC is ocean thermal energy conversion, and SWAC, seawater air conditioning. And the little inset there showing the graph of its temperature versus depth. basically, you know, through the depth of the water column, you can see there the kind of profile, and that's just, you know, an example. It changes depending on where you are in the world, but the theme is the same. It tends to be quite warm at the surface, particularly in the tropics, and pretty cool down deep, 4 or 5 degrees C. And so we can use that temperature difference, which might be 20 or 25 degrees, to do something with it. So let's move on to the next slide. So a couple slides here now we're going to show you on seawater air conditioning. And so the concept here is to basically replace a conventional cooling plant, which might have mechanical chillers that are usually electrically operated, and replace that with basically a set of titanium heat exchangers and a deep ocean pipe and some pumps. So you can see there the cartoon on the top left shows you the concept there. So we've got a seawater intake coming down from the deep, coming up from the deep. We bring cold water, we put it through the cooling plant, and then it gets circulated to the buildings in a very similar way to what would happen if you had mechanical chillers in that cooling plant. And so what that does is, in effect, moving to the two kind of comparisons on the right here, conventional AC and the graph above it. Very low fixed cost, relatively speaking, but of course we're at the mercy of electrical rates. So that's the yellow, and you can see, you know, electrical rates aren't expected to, you know, fall significantly anytime soon. And so, you know, that gives you the kind of overall feel for the cost. And then moving to the right, the benefits here of seawater air conditioning, quite a bit of fixed cost, but you've decoupled yourself from you know, cost escalation on the electrical rates. So the main components for seawater air conditioning, you need offshore pipes, so you need access to deep water, some pumps, some heat exchangers, and the chill water loops. So this is a technology, I think if we move to the next slide, this is an example. So this is a technology that is commercially viable and exists. There are a number of projects now around the world. There are probably only a handful of seawater air conditioning projects, but there's some pretty large lake source cooling projects. The downtown of Toronto has 3 large pipes that go to the bottom of the lake and cool the city in the summertime. The Cornell campus has a lake source cooling system. There are quite a few examples, and even some in Europe. But this is an example in Tahiti, in Bora Bora, where this is a Makai design. Basically, a down the slope pipeline brings up cold deep sea water at about 900 meters, and it cools. And basically, it was installed at the same time as a set of those very lush bungalows that are you can see on the top right within the atoll, and it cools the hotels, buildings, and the bungalows. And it's a very good system, and it's been operating for a number of years. And it's a good example, albeit this one's quite a small system, but it is nevertheless commercially viable. So that's seawater air conditioning. So now that seawater air conditioning is kind of the little sister, I guess, of OTEC. Moving to OTEC, Ocean Thermal Energy Conversion, just to give a sort of 101 of this one. It's actually a technology that's been around for a long time. So French scientists came up with this one in the late 1800s. And basically the concept is we can generate electricity by exploiting that difference of temperature between between the hot source, the surface ocean water, and a deep cold sink. So the deep water down, you know, sort of about 1,000 meters deep typically is when people refer to deep ocean water for OTEC. So that's the basic concept, and typically using a Rankine cycle, as a typical heat cycle to do it. Not really any different than an air conditioning wall unit. So if you imagine you think about a wall unit that cools your room. If you sort of think about that in reverse, so if you had, on the outside some hot seawater and on the inside some cool seawater, then instead of taking electricity from the plug on the wall, it would be putting electricity back in. So it's kind of a very crude comparison, but that's the concept. Okay, so moving on now to the talking about the resource. So What's interesting about OTEC, and I think very valuable and desirable, is the base load power. So a lot of renewables that we have are intermittent. So the wind doesn't always blow, the tides aren't always flowing, but OTEC is 100%. I mean, it won't ever be quite 100% because there's always sort of maintenance intervals and things, but it is 100%. It's base load power. We can operate it night and day, year round. And some of the other kind of desirable features of OTEC on the left there, it's a pretty big resource. The map here, which is showing the heat map, what that map is showing you is the best areas for OTEC. So the red and the pink and red areas, or orange and red areas, are the best. That's where the biggest temperature difference between deep and shallow exists. So you can see we're in the right area here that we're talking about, and a lot of us are located. And it's a green technology, and also there's potential for secondary products such as desalination. Not always. There's a caveat to that one, and it really depends on whether we're doing onshore OTEC, offshore OTEC, and we'll touch on it again shortly. Now, let me just take a breath and just check that everyone is still there. I don't know. Can you still hear me? Are you still seeing, Steve?
Yeah, we're all good. Richard, go ahead.
Lovely, great. Okay, so let's talk now about that onshore versus offshore OTEC, because there's sort of two flavors to OTEC. As a backdrop, the dilemma is that the necessary thermal gradient is found at sea. So you need to be out there, you need to have the depth of water, but the power it can generate is needed on land. So we have this sort of two choices. We can either be onshore, where we can, everyone knows going offshore, is twice as hard, twice as expensive. So it's nice if we can build stuff onshore. However, it does mean we've got to bring huge quantities of seawater ashore. So we need very large pipelines and all the sort of risks associated with pipelines that cross, shoreline. The opposite to that is we can go offshore, and so we can build ships at sea or platforms at sea, where the temperature gradient, the deep and shallow seawater is pretty close by. It's just underneath us, and we can send the electricity to shore instead. This is generally accepted to be the economically viable option when we're looking to build out utility scale. Just really one of the biggest things is just the pure quantity of water. I mean, we're talking in the sort of tens or hundreds of megawatts of plant. We're talking about bringing, which is power station size, utility scale, hundreds of megawatts. You're bringing in sort of quantities that I think, will probably be comparable to Niagara Falls or something like this. It's a significant undertaking. So I think, small scale OTEC and niche activities onshore is pretty good. But as soon as we're talking about power stations, I think we're talking offshore. Okay, the OTEC history. Again, I mentioned it's been around for quite some time. Following the images left to right, there's Jacques D'Arsenval there on the left. He's the guy that's attributed as the grandfather of OTEC. And the guy called George Claw was quite interesting. He actually built some steel pipes from Cuba, and he had a couple of failures and one success. But it was interesting he was working so early on. In the middle there, that's Mini OTEC. That's a 50 kilowatt demonstrator that's built off Hawaii. I think it was in the 70s. And there's a lot of work done by US government, Department of Energy. Some corporations jumped in as well, like Lockheed Martin, in the 70s, and then in the 80s came along, and things changed and funding was cut, and it kind of went quiet for some time. And then late 90s, 2000s, things picked up again, and again, specifically in Hawaii as well, we had a lot of activity, and we have the precursor, and then eventually the Natural Energy Lab of Hawaii, which is a real center of excellence on the Big Island here in Hawaii. I think it's been a number of decades in the making, but now it employs something like 600 people, 800 people. A lot of them are high tech or academics, and there's some viable commercial businesses using the deep sea water for a number of different applications, and OTEC is one of them, heat exchanger research. And I think I read somewhere that the annual tax contribution is several $1 million just from Nelhard, so that's pretty good. Yeah, so moving to the next slide. In the next couple of slides, we're going to talk about the kind of development. So here is a map showing you a bunch of different operational, planned, proposed OTEC projects. But the fact is that there's really only 2 plants that are operational just now. There's one in Okinawa, which I'm not even sure is operational, but it's very comparable to what we have in Hawaii. They're both onshore OTEC plants. And then there's some names of some companies on the right here, just to show there's been quite a few, and some of these are large. Lockheed Martin, Naval Energies, Bardo, they're all relatively large companies that have got themselves involved in OTEC at one point or another. So here, next slide. This is really just to demonstrate some of the different concepts that have come through over the years. And there are plenty more as well, but there are different sort of platform concepts, and a lot of it leverages on oil and gas and some of the technology that's been developed there. So there's no shortage of good ideas. Then moving again, just to sort of try and show some steel. I was going to say steel in the water, but this isn't in the water. This is a onshore research facility that my company developed, and we finished in 2015. It's now mostly used, this facility is mostly used for heat exchanger development, but we were running an OTEC plant. It was the world's first grid-connected plant, but it's been a real gem, a really useful research platform. Again, this is steel in the water. This is showing a 1 megawatt floating plant. And this is really a big milestone. Unfortunately, because of COVID and things, I understand that they haven't actually done all the testing they wanted to do, and I don't think they brought it to Kiribati in the end. But they did a bunch of testing off Korea. But this is a 1 megawatt. The takeaway from this is that it is possible as you start to get bigger in scale. This is a 1 megawatt floating OTEC plant, and I believe it was successful. Moving into cost, which is kind of one of the challenges of OTEC, it has very vigorous economies of scale, which is the problem. It's a chicken and egg problem, because no one really wants to build a pilot plant. Certainly if we go back to that one, sort of megawatt scale, other than research, something of that scale is not really economically viable. It needs to be big. There's definite chicken and egg, or economies of scale. However, when we look at the sort of cost projections, and that's what this simple figure is showing, green bars are OTEC, so a smallish plant, 100 megawatt, fairly large, medium to large size plant. We're looking, this is dollars per megawatt hour, or it could be dollars per, it could be cents per kilowatt hour, if you drop a zero off it. So basically, what we're trying to show here is, I think this was from some modeling we did for a small island, tropical island state. We think OTEC can be competitive from the outset with diesel generation, which is what a lot of islands are using diesel. It's probably not quite to the point of competing with wind just yet, but bearing in mind wind was far above those green bars at the outset 2 or 3 decades ago. So we've seen the cost of offshore wind come down very drastically. So this is today. So we think with significant cost reduction efforts around heat exchangers, the cold water pipe, the platform design, those green bars do have potential to come down further. And also we can look at larger plants. So I think it does show promise as grid connected, in the long term against wind, which is doing very well. So the submarine challenges just on the kind of SWAC and OTEC parts, and so I'm just going to go through these, and that'll sort of conclude the kind of OTEC part in the sense, the conventional OTEC, grid-connected OTEC, and then the next few slides I'm going to get in a little bit about the grazing opportunity and how it might fit into the hydrogen economy. So just to take you through this, I think, again, to make a comparison, you know, SWAC and OTEC are different. The SWAC, I think, is technically mature. It's I think, proven. There are a number of successful projects now, and you know, I think anywhere where you've got a pretty decent air conditioning load, you know, it's obviously going to be in a tropical part of the world that is fairly close to the shore, to the ocean, and has pretty good access to deep ocean water. Seawater air conditioning is attractive, especially for new build projects. I think, you know, there are a number of big resorts and districts that are being built close to the ocean, and I think, you know, it's not just direct seawater cooling. So there are different flavors of SWAC. I should say this, that, you know, there's sort of hybrid options where even if you can't get to deep seawater, you can use relatively shallow water to greatly enhance the efficiency of kind of conventional chillers. So there's that to bear in mind. But so then comparing that to OTEC, I think, you know, OTEC is it's a sort of step on. You know, we're trying to, the product is not coldness anymore. The product is electricity or something, energy. There's still some cost challenges, big economies of scale. Onshore is limited to small scale, and offshore, you know, the next step is really a floating pilot plant, a bigger than 1 megawatt pilot plant. And as we say on the right here, this image, you know, SWAC's problems are, you know, the challenges are retrofitting existing buildings. It's much better if you can get in on a new build. Onshore distribution, you know, that can be challenging, especially where, you know, there's streets to dig up and stuff. And then OTEC, the challenges there, and we'll go through it a little bit more, is cold water pipe and heat exchangers. That's sort of technical challenges. And then the common ones, you know, these are both pretty capex heavy technologies. Now, luckily, money at the moment is relatively cheap. So, you know, that's good. But the other issue too is permitting, and I mean, I think that's a common issue for a lot of projects around the ocean. But certainly that's kind of a summary of the technologies compared and the challenges. All right, I'm going to check in again, Steve. Are we still there?
You are, in fact, Richard.
Wonderful. Okay. There's nothing worse than you know, going along with a presentation and finding for 5 minutes and finding out that you've lost your audience. Okay, so I'm moving now to the grazing opportunity. What we got here is a pretty ugly slide. Apologies, it's a bit of an engineered slide, or I don't know what. But anyway, what we're trying to show here is the graphic on the left with the yellow and grey bars. This is showing the key components of OTEC, and key components of OTEC: a grid-connected, shore-connected floating plant. Now, what we're saying with grazing is we're going to disconnect from the shore, and we're going to take these offshore, and we're going to take our floating OTEC plants, and we're going to move them down near the equator, and they may have some form of station keeping or position control. Or they may be tended by a tug or something like this. But the concept is you have these floating plants that are not moored and they don't have a cable to shore, but they're producing electricity, you know, via the OTEC process. And then what do you do with that electricity? Well, it's stranded at that point. So what we would look then is if we got an energy carrier, so hydrogen, for example. Now, hydrogen is not necessarily the best transport fuel, certainly in my opinion, and so there are some other options. But just to conclude the thought on this graphic, so what I was trying to show here is, and the bars obviously are showing technical and economic risk, as it says. What I'm showing is with the grazing opportunity, you get to strike out in red some pretty big cost and technical challenges. So the cable to shore, that can be expensive. The mooring, also expensive. Permitting, that's not very expensive, but it's a big drain on a project timeline. And that's actually, time is money, right? So, I think we could really accelerate the deployment if we were able to streamline the permitting, remove the mooring, remove the cable ashore, and then sort of in parallel to that, what I've shown in the green dotted lines is not those aspects going away, but just saying, okay, over the last decade or two, we've seen significant technical advancement of these elements. Heat exchangers, well, we've been doing a lot of work on that in Makai, certainly. Others have as well, and there's some significant advances in this area. And heat exchangers can be 20 or 30% of the cost of an OTEC plant. And if you can cut the cost of those in half, which is about what we're seeing right now with the new developments, then you've knocked 10% off your capex, and so that's significant. And then you've got cold water pipe. There's been a bunch of work on that, and you can see the image there of that large scale with a chap standing next to it, a couple of chaps standing next to it. There's been quite a bit of advancement technologically there as well, and not necessarily in oil and gas. There has been some advancements in oil and gas, but also some independent kind of offshore advancements as well. And then finally, environmental impact. There has been quite a lot of academic work and also commercially funded work too, to kind of de-risk the any kind of pollution issues or permitting issues. And I think the general conclusion is OTEC is a pretty positive and green technology. So okay, next few slides we're going to talk a little bit about how we now, with our grazing plant, and I've got a cartoon there or a rendering of a possible floating, I think, offshore plant. We've got this thing floating around, or maybe we've got a fleet of these OTEC plants floating around in the middle of the, along the equator, riding the equatorial conveyor belt. How the heck do we get the power to shore? Well, hydrogen is something we looked at quite a few years ago, actually, at Makai with others. And so the next slides are very loosely based on some of that work and some recent updates to that work. So this was a project we did with the Department of Energy, integration optimization of hydrogen production with OTEC technology and offshore floating platforms. Nice, rolls off the tongue, that one, but that was the title of the project. And basically the question was, in a world absent of oil, in 2050, absent or expensive, is OTEC a credible H2 supplier? And so we did a bit of research on the hydrogen economy and the visions for that. I think, our conclusions were that a lot of benefits with hydrogen, but there are still challenges. And hydrogen is an energy carrier, it's not an energy source. And I think there's a lot of confusion sometimes on that point. And, one of the things we concluded is that Department of Energy's work, this is a few years ago now, just ignored OTEC. So we talked about other renewables and other sources, but hadn't included it. So we tried to fit the OTEC vision, and it is a big and ambitious vision, obviously, but you've got to think big, into the US Department of Energy's hydrogen economy vision. And so here, what they were looking to do is replace the fleet, or a fleet of 150 million vehicles. If you wanted to do that with hydrogen, how would you do it? And so here there's a table comparing possible sources of hydrogen. And so what we've done is we've just slipped OTEC in the bottom here and said, well, this is how much we need to do that much hydrogen. And it doesn't look crazy. I mean, it is between sort of 500 and 1,000 plants. I mean, that's, it's not inconceivable. So I think, it's an option. So then the next step really was, is hydrogen the best option as well for OTEC? And so we, as I said, we looked at the hydrogen economy. We looked at the other options. We said, is coal an option? No, not really. Nuclear, no. So we should look at hydrogen at OTEC. We think it's the only renewable really out of that list that has a massive potential for power production. It really is scalable. And we think it can be economically competitive with other renewables once we allow the sort of costs down that other renewables have had, like offshore wind, as mentioned, it could be there. And then the question is hydrogen the right answer? And certainly our conclusion from several years ago was no, probably not. Hydrogen is actually quite a inefficient energy carrier. It has its applications, and I think it's smaller scale, possibly hydrogen cars and hydrogen planes, that sort of thing. But in terms of shipping very large quantities, it's not necessarily the best. And not to say that it couldn't be done. I think technology, moves to fill the, to make it work. But I think looking at it today, we felt that ammonia was actually a very good intermediate step. It's a much more, it's much safer. It's much, it's just much easier. It's more, people are more accustomed to transporting that that material, and there are some other advantages too, which we'll get to. And so the overall kind of thought in terms of OTEC fitting into the hydrogen economy, OTEC has challenges, but so does the hydrogen economy. I think most people that know a little bit about the hydrogen economy probably already recognise that, but just to reiterate. So here, next few slides talking about ammonia as the energy carrier. So the idea here is that we generate electricity with OTEC, and then on our we've called it an FPSO, the big grey box. We're basically we've got a small ammonia production plant, and ammonia, the molecule is nitrogen and hydrogen. So we've got nitrogen in the air. That's fine. We can use an air separator. We've got plenty of hydrogen in the water. We can electrolyze it, and we can make ammonia. And what people don't appreciate, I think, is that ammonia is an extremely important molecule or compound. It's actually, if it wasn't for, I think it was Haber-Bosch that came up with the ammonia synthesis kind of process. I read a book once, and basically the upshot of the Haber-Bosch coming up with that is actually saved us all from starving to death. I mean, it's just to say it in a very blunt and crass way, but it basically feeds the world. And at the moment, if we didn't have fertilizers such as ammonia, we wouldn't be able to make food fast enough and enough food. And the interesting thing at the moment is that most ammonia is coming from natural gas. So a lot of people don't appreciate this, but a lot of the food we're eating is natural gas. A bit of a simplification, but it's an important molecule. So move to the next slide here. So again, the slides are a little bit jumbled actually, but this sort of shows the big picture concept. So West Pacific, East Pacific, and the three areas here, and just sort of showing, where we'd have the plants pretty far offshore, and we could ship ammonia in this case to market, to shore pretty easily, in a very similar way to probably LPG, and it's a very similar sort of a product to move around in shuttle tankers. So this one's talking about the logic of the ammonia industry. So we'd have production and storage offshore, and then shuttle tankers to take it to shore, and then we'd have to have shore terminals and distribution. And the ammonia could be basically sold directly into the ammonia market, or it could be cracked back into hydrogen and put into the hydrogen economy as the hydrogen economy develops. So the takeaway, I think, from this slide is to say, two things really. One, a fair amount of infrastructure is needed for something like this, but book them and they will come. And the second thing is, there's potentially, if we use ammonia as the energy carrier, there's sort of two options. We can sell it directly, or we can crack it and use the hydrogen. I mean, there's some energy losses in cracking, but from our analysis, we think it's worth doing that, to fit in with the hydrogen economy. So, and so here is on the right hand side is sort of showing you the fleet, we need about 700 plants if we built 400 megawatt fleet. So this is obviously big picture stuff, but I wanted to put this across. Oh, sorry. And then looking at some costs here. So for a 400 megawatt plant, we're roughly talking, these figures are 1 or 2 years out of date now, but it's going to be pretty close. For a 400 megawatt plant, we were talking about $2.5 billion. It's a pretty sizable investment, but as I've heard people say, the fuel for OTEC is free, but of course, it's also $2.5 billion that you've got to service the debt on. So, and then here the pie chart is showing you kind of a breakdown of the costs, and you can see, as I mentioned before, heat exchangers is a big part of the cost. So structure is obviously important, but this is factoring in, the ammonia production and even the shuttling. So, it's interesting that those become a relatively small cost. Okay, and then this is showing you the cost of hydrogen in dollars per kilogram, and so this is sort of assuming end to end. I know we're jumping back and forth a bit from ammonia to hydrogen, but this is assuming we're making electricity with OTEC. OTEC is making ammonia. Ammonia is shipped to shore. Ammonia is cracked to hydrogen and is sold into the hydrogen market. So this is considering all of that. So it's showing you the cost per kilogram. So that's the green bar for OTEC predicted against some other options: nuclear, waste energy, wind, solar, wave. And you can see we're in the ballpark. I mean, it looks pretty good. We're perhaps not quite there against wind yet, and I would say this is several years old, and probably wind is a little bit lower now. So we've got a competitor. So and then moving to the bottom graph, it's just sort of showing you in a separate way cost of hydrogen, and this is projecting. So the darker red is future, and then the present day is with the additional kind of salmon color on top. So so you can see, again, big picture, OTEC's in the ballpark and it should be considered. So all right, I haven't got too many more slides, but I think 3 or 4 more slides, and then if you're all still there, we'll maybe get to some questions. So this is now talking about ammonia as a direct product. I mentioned this. So some 3 graphs, and these data are a little bit out of date, but so it's taken from an older paper. But I think it showed what I wanted to show, which is since the 1960s here on the top left graph, this is plant nutrient consumption. So you can see, we're going up. Millions of tons of fertilizer is used every year, and then moving to the top right, this is US ammonia production capacity. Hey, that's going down. so that's interesting. And then the bottom one is probably the most interesting graph. This is dollar per ton of ammonia, and on the right hand side, dollars per for natural gas. And so you can see natural gas is the blue line. And you can see it moves around a bit, but it tracks, the cost of ammonia naturally tracks natural gas. It would do, because most ammonia is made from natural gas. But you can see the trend has been, certainly in the early 2000s was increasing. And wow, I just looked it up for 2022. We're up to about $1,000 per ton of ammonia. So what was pretty desirable at $300 or $400 a ton, I think, when we were doing our analyses, is definitely going to look pretty good right now. So yeah, is there an opportunity to sell OTEC ammonia, is the question we're posing. Okay, so now just sort of come to the conclusion of things. So OTEC, we can make electricity with OTEC. That's in the first instance. And then what's the next thing? If we go with a grazing option, is ammonia the energy carrier? It could be a very good energy carrier. Technology exists already. It's pretty low technical risk, I would say, actually. Whereas making direct hydrogen, I don't think is that low technical risk. I think the idea of remotely making hydrogen and trying to ship that from the equator to all these places, I think there's still a few sort of challenges and risks with that. So I think the idea is maybe make ammonia, and then it can be cracked for hydrogen as and when the hydrogen economy comes along. And in the meantime, it could be ammonia sold directly to market. So some just points to finish up. OTEC is technically feasible. I think in the grand scheme of it, the technical risk is actually quite low with OTEC. It's not, there are still one or two challenges, but it's not, like some divergent renewables, I think. It's economically viable for electricity today. I think if built at scale, and especially for markets where we're paying a lot for electricity already, remote island communities, it looks pretty decent. I pay 32 cents a kilowatt hour for my electricity. So ammonia looks promising as an intermediate energy carrier. And the last point, in the hydrogen economy, OTEC should be considered alongside other renewables. It's a large sustainable resource, continuously available. It is baseload power, it's just a key one, and it can be cost competitive. Okay, so the last slide I'll leave you with here is this kind of next step. Well, okay, how do we get to this 2020 vision, of 700 plants? How do we make this happen? Well, in 1970s, we put a 50 kilowatt floating system in. 2019, we put a 1 megawatt system in, and there's been a variety of other onshore and offshore tests and de-risking. And I think we're ready now to move to a medium scale grid connected pilot plant, probably around 10 megawatts in size. And it could be, I think, cost competitive with other renewables. Question to pose is, where? Do we do this in Hawaii? I mean, certainly we've talked a lot about it, or somewhere else. So, yeah, so that's it. So I think the moral of the tale here is that, we think OTEC is extremely promising renewable technology. It's just really held back by the kind of chicken and egg of being very cost competitive at very large scale and not so much at small scale. So, okay, well, that's it. That's my presentation, and yeah, I probably ran a few minutes over there, but if you have any questions, I'd be happy to take them.
Thanks a lot, Richard. If you don't mind, I'll let Alex Burrell ask the first question.
Sure.
All right, thank you, Steve. That was very interesting. What I'm wondering is what type of long-term studies have been done on the environmental impact of, because I'm assuming that it changes the thermal temperature in the ocean. If you could elaborate a little bit on that.
Yeah, sure. So I did mention that as well. So there have been a number of studies last couple of decades on the sort of mixing and the implications, because there's really two things you're doing. One is you're bringing up, you're doing artificial upwelling, essentially. You're bringing cold water up and putting it in nearer to the surface, and you're also bringing up water that has is much more rich in nutrients. So I think on those two points specifically, the thermal issue is actually less of an issue, I think, than first thought, and a couple of reasons for that. Firstly, that cold water, when it's returned, usually it's not returned right at the surface. It'll be returned, let's say, 50 meters down. If you go that sort of depth, you're already below the photic zone, and it tends to be, because it's cooler, it's more dense, and if it's also ejected, sort of pushed, vertically down, it actually sinks very, very quickly. So it from the modelling that I've seen, you don't have that, providing it's discharged, the return water after the cool water has been brought up, and bear in mind it's warmed up a little bit too. So it is warmed up a little bit. Then it's discharged, as long as it's discharged below the photic zone, and actually even if it's not, the modelling I've seen is it falls away very rapidly back down to deep ocean waters. And so that's on the thermal. And Also, I think it's I hate to say this, but it really is a drop in the ocean. It's a very, very small. Even if we built 700 plants, it's still a relatively small kind of thermal delta. Not to be sort of dismissive of it. I think if and when we got to the point of rolling out 700 plants, I'm sure there's a lot more analysis needs to be done. On the nutrient point, which actually I think is a more important in some ways. What we don't want to do is create huge algal blooms or something like this. But again, the key thing I think is keeping it out of the photic zone. And there is some argument to say actually we should do that and actually try and create artificial upwelling and create algal blooms, and because I mean actually I'm no expert on this part, but if you're increasing productivity, you're effectively capturing carbon, and these big algal blooms or big productivity would then fall away to the bottom of the ocean at the end of its life cycle. So there's some interesting points there. Is there a carbon capture opportunity if we were to direct the discharge nutrient rich waters into the surface? So but yeah, it's not my area of expertise necessarily, but certainly, sorry if that's a slightly longer answer, but I think the bottom line is, from what I've seen, I'm personally not overly concerned about it. I don't think it's a huge.
Thanks, Richard. Nick, you had the next question.
Thank you, Steve. And Richard, thank you for a really cracking overview. I thoroughly enjoyed that. Really interesting. And it's the first time I've seen grazing explained so comprehensively. Can you talk a little bit more about the business model and how you scale this? Because has any work been done, for example, to show that wind started off being heavily subsidized by government to make the numbers work? Which sounds as though OTEC hasn't got to that stage yet. So, so logically, to get the scale of power generation that you talked about, you're going to have incentivization. And then the other elements that have been in my mind is how do you compare this with savings that or additional benefits you could bring to the environment, such as the infrastructure providing natural habitats for marine life and so on. If there's any study being done around that, I think the interest we have from a MARES perspective is how do we create a business model that makes the technology scalable and worthwhile?
Yeah, no, thanks for your question. Yeah, I think on the first one, yeah, I mean, it would be perfect if we could get a big government support. The real issue, I think, is this this economies of scale. I mean, I used the term chicken and egg a couple of times, which I kind of hate, but it's true. With OTEC, it's not quite like any technology goes through a scaling scaling phases. The first oil tanker was a sailing ship with 10 barrels on its deck. But I think the problem with OTEC is that you kind of need to spend a few $100 million to even get to the point of showing an at scale probably 10 or 20 megawatt plant, and yeah, I think it's just been hard to sort of get that first big increment. I mean, there's an awful lot of good funding in the 70s, the sort of pre-Reagan era. There's an awful lot of funding. There was even legislation, it still exists today. There's actually an OTEC, a piece of US law, the OTEC Act, I think it's called, or something, and there was a huge amount of work that was done, but it just wasn't quite enough. They cut it off. There was, I think, an image earlier in my presentation. I'm not sure if you saw it, but it was next to the mini OTEC picture, and it showed a larger ship with a bigger demonstration plant, and they actually didn't get all the way through that. So I think it was a real shame it got kind of cut off, but seems like there's been stops and starts with OTEC, and I think it does. To answer your question, I think it does need a big help, big subsidy, something, because as you rightly say, wind and even oil and gas, they've all had sort of subsidies or help along the way, and I think that's kind of what OTEC needs. I do think probably there is a stepping stone. I think the ideal thing, I mean, to my mind, is if somewhere like Hawaii with expensive electricity, was able to build let's say a 10 megawatt plant, as I've said, and connect that to the grid, a floating plant of that sort of size. I think people then start to pay attention, and I think it would show another point on the graph and some evidence that we could get there with a even bigger plant. So I mean, I don't have a very good answer for you, I think, in terms of commercial.
No, it wasn't a very well given question either. The issue in my mind is, have there been any studies which say we had to incentivize wind to this extent to achieve fixed offshore wind or floating offshore wind? And therefore, when you look at the scaling of the OTEC business model, is it a comparable number? So we had to spend this much to get wind out there. We're going to have to spend a similar amount to get OTEC out there, or it's going to be even bigger. But set against it, and you only really mentioned it early in your presentation, is the fact that OTEC is permanent, as near 24/7 available energy as possible, which is not the case with wind. So there's a number in there that works to benefit as well. I won't bang on about it. I just think I would love to know if there's any studies or where to go and find studies that said to make offshore wind work, we had to spend this much, and that would equate well with what we would have to spend to make OTEC work.
Yeah, I have. Interesting. I haven't specifically on that. I haven't seen any work on that, and I don't really know what the numbers are. But I think you did bring up a point just then. Again, the baseload power. I think that's such a key one. There's no other renewables that have that, and we've got issues with intermittent renewables like wind. It's a theoretical maximum before we going to get into sort of curtailed energy issues. I think that's the crown jewel of OTEC, really, is the fact it could be baseload power. I think it's so key.
I'll shut up, Richard, because there's other people with questions, and mine weren't very well asked.
That's all right. No, it's getting later for me, so I'm probably not answering too well either.
Thanks, Nick. Jin Mao, you're next.
Yeah, thank you. I have one question regarding the ocean's thermal energy conversion technology. So for this technology, the necessary thermal gradient is the key factor for this technology. So I'm not sure the gradient will be changed over the time. So how to ensure this gradient will not changed once the infrastructure is built?
Yeah, thank you. Yeah, that's a really great question. It highlights the key factor. You're quite correct. That thermal gradient is everything. It defines the thermal efficiency of the plant, which by the way, the OTEC, when you consider it as a thermal cycle, is extremely poor. I mean, it's worse than a in terms of thermodynamics, it's actually worse than a late 1800s Thomas Newcomen steam engine. I think it's only a few % thermal efficiency, Carnot efficiency. But we're using free fuel, so we got that in our favor. Now, in terms of answering your question, actually what we have, that thermal gradient, is a surprising variation just during the year. So I don't think that was your question. I think your question was longer term. But we actually deal with quite a surprising variation during the year. So that obviously has to be taken into account for the design of the plant. What I mean is, and it's mostly just a variation in the surface temperature. What I mean is that, in the summertime, we might be on a nominal 10 megawatt or net 10 megawatt design plant, we might be generating 12 megawatts, but in the winter we might only be generating 8 or 9 megawatts. So there's that sort of nuance to the design to keep in mind. But I think what you were asking is probably on the longer term, so but maybe with changes in sea temperature. If anything, I think I've seen surface sea temperatures perhaps are rising subtly, and depending on where we are, but I think that's going to be quite a small change, even just even like a period of 50 years or so, or even 100 years. I don't think that change is that significant compared to even just the seasonal change we'd have to design for.
Okay, thank you for your clarification.
Okay, thanks, Jin Mao. Ben, the floor's yours.
Yeah, thanks, Richard, for the great presentation. And I don't know if you saw I thought I'd be efficient and put my long point in the chat box, but I'll summarize it. So in the Marshalls, where I'm in the Marshall Islands, we had around 2008, 9, 10 extensive discussions and plans with the Professor Hans Kroc. I don't know where he is nowadays. He was at University of Hawaii, and there were some tentative plans to build an OTEC plant here in the Marshalls, either near the base, the U.S. base on Kwajalein, or the island next door, Ebi, or here in Majuro. And the whole idea there, exactly as you had said, is that these atolls are in very deep parts of the ocean, so there's a big gradient, and the shallow, warm lagoons are additional benefit. So everyone at that time thought, okay, this is something that's going to be, as was discussed earlier, initially subsidized, but hopefully commercially viable thereafter. And what further convinced us was we had some discussions with the U.S. Navy engineers who said, yeah, this thing is going to be piloted by us at some of our bases near the equator, starting with Diego Garcia, but they are also looking at Kwajalein at some point. And then fast forward a few years, and then just everything just sort of fizzled out. And so I'm just wondering what happened over these years, and are the prospects, in your view, much better now for revisiting some of these plans, especially for some of these remote countries like the Marshalls? Thanks.
Yeah, thanks, Ben. Yeah, and apologies everyone, because I'm just now catching up with the chat questions and comments. I was obviously sharing my screen, so I as you were posing your question, Ben, I was reading your question there in the chat. Yeah, so I'm quite familiar actually with Kwajalein and Marshall Islands and Hans Kroc. Yes, familiar as well. I think for decades we've been trying to get something happening in the Marshall Islands in Kwajalein. I know even before my time, our founder, oh gosh, I think probably in the 80s, I think he was down there in Kwajalein trying to get something moving. So I know a number of people, and you mentioned Hans Kroc. There are a number of people who've been trying to get something going there, and even recently, I was actually there. Oh, let's see, 2 or 3 years ago. So the army base in Kwajalein, they were at the time looking at an energy savings performance project for the base, and we weren't looking at OTEC specifically at that point. We were looking at SWAC actually. Unfortunately, that project, for a few different reasons, has halted, which is a real shame, because it seemed to me a total no-brainer. And again, the same is also true with Diego Garcia. We worked with the Navy there via Lockheed Martin, actually, which were actors over there, in a similar level, again for SWAC. So that's recently. So predating that, I think you mentioned OTEC a number of times in these places. And the Navy has also been quite active in past years, trying to push marine renewables, not just OTEC, but renewables in general. They've been trying quite proactive. We have in Hawaii, off the Marine Corps base, the Wave Energy Test Site, for example, and they've been quite active in other places with OTEC. Short answer, I don't know why it's sort of all suddenly died a death, but it seems to sort of come and go. And I don't know if that's a sort of partly a politics thing, or partly, price of oil as well, I think, also bears a, you know, it's a shame because it seems to sort of ebb and flow. But I know there has been some renewed interest recently in OTEC, but yeah, I guess I don't know. Don't really know the answer to the question. I think, are the prospects better now? I'm not sure.
Thanks, Richard. We're running out of time. I just have one final question for you. And it goes to next question about business models. I think everybody seems to be obsessed with cooling and energy. Is there any value in your business model for nutrients and the impact of being able to provide? I know in Hawaii there is you have a related desal and aquaculture business co-located near what you're doing. Could you just talk about that for a minute or two?
Yeah, I think that's a good idea. Just as well, because I think it's a nearer goal too. So I think, you know, what I presented today is, you know, a pretty ambitious and long-term vision, you know, getting to 2050 and many offshore plants. It sounds a bit abstract, and, you know, but I think trying to bring it back to, you know, something that could be a quicker flash to bang. Yeah, something along the lines of NELHA, the Natural Energy Lab of Hawaii. You know, for some, perhaps one or two island nations, you know, I know others have looked at it. Places like Puerto Rico and such have considered it. But I really do think there probably is an opportunity for that sort of what you mentioned. You know, a co-located, you know, a number of different oceanic enterprises or industries in one place. I mean, as I mentioned right at the beginning, NELHA to me has been a big success story. I mean, 600, 800 people employed, something like that. You know, I think several $100 million of associated, you know, money coming in and out, and a huge amount of academic research. It's a success story. And so, you know, something like that where, you know, this cold, deep ocean water, yes, we could have an OTEC plant, but that could just be one piece of it. You know, we could definitely have an OTEC plant and sort of research facility. We could also have, you know, they have a lot of aquaculture activities at NELHA. They have people making, you know, spirulina. They have people growing abalone. They have desalination and bottled water with some of the salt water left in. And, you know, I'm just trying to think what else they have. I mean, they have a whole research park. And the research park is air conditioned with the deep seawater, and the heat exchanger they do it with is probably, you know, the size of a, I don't know, half the size of a car. You know, it's very small. And so I think something like that, you know, could be a quicker, you know, oceanic industry, deeper ocean industry kind of development, you know, in partnership with academia and etc. That could be pretty good to sort of try and duplicate that in a few different places. You know, it has taken a long time to get the National Energy Lab going, but it's where you've got access to deep seawater, it makes a lot of sense. So I think that could be one thing, you know, where you want, you know, there's different products in different industries. Yeah.
Thanks, Richard. So I think the outcome from this is we probably need to talk to NELHA next, right?
Yeah, I think yeah, I think so. I mean, I think that would be interesting. And as I say, there have been a few attempts to launch something like this in some other locations. So I know there's interest. There's a lot of interest. I think places like Mauritius and I think Puerto Rico, they have had sort of embryonic ideas of doing something similar. But they're not to also take away and distract from, you know, electricity and hydrogen and OTEC. I think, you know, there is a next step there as well for you know, a medium-sized floating plant. I think, you know, there's definitely an opportunity there, especially when I think one of the comments here, did I hear correctly that you're paying 32 cents per kilowatt hour? Yes, what I meant was, though, that's what I pay in my house from HECO. That's the residential electricity rate just now. So I think my point is that, you know, island nations like Hawaii, our electricity is very expensive. So, you know, the bar is high. the opportunity is desirable, you know, so OTEC could look pretty good in a place like Hawaii.
Okay. So on that note, I'm going to say thank you very much for your presentation, and I expect that the folks from NLIA will contact you and follow up with you to do some more work. And I thank everybody for coming and joining this call, and I look forward to seeing all of you at the Healthy Oceans Tech and Finance Forum 26th to 28th of January online. So thank you very much, everybody.
Yeah, and yeah, thank you all for joining. It was a pleasure to give the talk.
Thanks a lot.